to 3,000 words. Conversely, bigger models like GPT 4.1 and Gemini 2.5 Pro offer context windows up to 1 million tokens, which is equivalent to roughly 7,500 words or 50,000 lines of code. So, as you can see, choosing the right model for the task can be very important. For example, if you downloaded a novel in a TXT format and you wanted to change the script, choosing a model that offers a large context window would be best. Conversely, if you're working on a small document and require very low latency, meaning faster responses, using Flash and nanovariants would be best. Here's another angle to look at when it comes to memory in LLMs. Let's say I asked you this question. Sally and Bob own an apple farm. Sally has 14 apples. Apples are often red. 12 is a nice number. Bob has no red apple, but he has 2 green apples. Green apples often taste bad. How many apples do they all have? This might require you to think about the problem a little bit to get to the final answer, which is 16. That's because the context here includes information that is completely irrelevant to the question, which is to count how many apples they have in total. The fact that apples are red or green or how it tastes have nothing to do with the total number of apples that they have, because they either have the apple or they don't. Now that we have a grasp on what context window provides, TechWorks' 500 gigabytes of documents, this creates an immediate problem. Even the largest context window, like Gemini 2.5 Pro's 1 million tokens, can hold only about 50 files of typical business documents all at once. We need our AI model to understand all 500 gigabytes, but it can only see a tiny fraction at a given moment. This is where embedding comes in, and they're absolutely crucial to understand. Embeddings transform the way we think about information. Instead of storing text as words, we convert meaning into numbers. The sentence employee vacation policy and staff time off guidelines use completely different words, but they mean essentially the same thing. Embeddings capture that semantic similarity, and here's how it works. An embedding model takes a text and converts it into a vector, typically 1,536 numbers that represent the meaning. Similar concepts end up with similar number patterns, like vacation and holiday will have vectors that are mathematically close to each other. For TechWork, this means that we can find relevant documents based on what someone means, not just the exact word that they've used. When an employee asks, "Can I wear jeans to work?" our system will find the dress code policy, even if it never mentions the word jeans specifically. Now that we understand how LLMs and embeddings work, we will need a system that ties everything together. In our case, TechWork needs a chatbot where customers can ask questions about company policy, product information, and support issues. The chatbot needs to remember conversation history, access the company knowledge base, and handle complex multi-step interactions. Your first instinct might be to use OpenAI's MCP to build a quick chat interface, but you quickly realize that there are massive instances storing chat messages, maintaining conversation context, connecting to TechWorks' internal knowledge base, and handling the possibility that the company might switch to OpenAI to Anthropic or Google in the future. And now, what seems like a simple project becomes a massive undertaking. While you can write your own implementation to connect them, there's already a well-established abstraction layer called LangChain. LangChain is an abstraction layer that helps you build AI agents with minimal code. It addresses all those pain points using pre-built components and standardized interfaces. But first, let's understand the crucial difference between an LLM and an agent. When you use large language models like GPT, Claude, and Gemini directly, you're using them as static brains that can answer questions based on their training data. An agent, on the other hand, has autonomy, memory, and tools to perform whatever task it thinks that is necessary to complete your request. For TechWorks' customer support scenario, imagine a customer asks, "What's your company's policy on refunding my product that arrived damaged?" An agent will self-determine how it should answer that request based autonomously instead of traditional software that requires conditional statement that determines how a program should execute. LangChain comes with extensive pre-built components that handle the heavy lifting. For TechWorks Chatbot, LangChain chat_models provide direct access to LLM providers. Instead of writing custom API integration code, OpenAI with open bracket model equals GPT-3 Turbo. So if the requirements change to use Anthropic instead, you simply change one line, LLM equals chat Anthropic, open bracket model equals Cloud 3 Sonnet. This same pattern applies to every other capability TechCorp needs. Memory management uses Memory Saver to automatically store and retrieve chat history, which means there's no need to build your own database schema or session management. Vector database integration works through standardized interfaces. Whether you choose Pinecone or ChromaDB, LangChain provides consistent APIs, and we'll go through what a vector database is in the next couple chapters. For text embedding, it uses OpenAI embeddings or similar components to convert TechCorp's document into vector representation. The embedding process becomes a single function call instead of managing API connections and data transformations manually. Finally, tool integration allows the agent to access external systems. So if you need to query TechCorp's customer database, you can simply create a tool that the agent can call when it determines customer-specific information is needed. Without LangChain, you would need to build all of this infrastructure yourself. API management for multiple LLM providers, vector databases, SDKs, embedding pipelines, semantic search logic, state management, memory system, and tool routing. The complexity grows exponentially. LangChain's component library includes modules like Chat Anthropic API connections, ChromaDB vector database operations, OpenAI embeddings for text-to-vector conversion, Memory Saver for chat history management, custom tool definitions for external system integrations. The agent orchestrates these components based on the conversation context. So as we're talking about TechCorp, depending on what the question is asked, the agent will now use the given tools like vector databases as well as the context it built from conversation memory. And the system prompt written in the API layer autonomously handles your request. And you can extend the agent's abilities beyond this example by using other pre-built tools that LangChain offers, like custom database access, web search, local file system access, and more. Now that we covered the conceptual elements of LangChain, let's look at how it looks like on a practical level. We can look over at this lab specifically geared towards how to use LangChain. Alright, let's start with the labs. In this lab, we're going to explore how to make your very first AI API calls. The mission here is to take you from absolute zero to being able to connect, call, and understand responses from OpenAI's APIs in just a few progressive steps. We begin by verifying our environment. In this step, we're asked to activate the virtual environment, check that Python is installed, ensure the OpenAI library is available, and confirm that our API keys are set. This is important because without this foundation, nothing else will work. Once the verification runs successfully, the lab will confirm that the environment is ready. Next, we take a moment to understand what OpenAI is. Here, we're introduced to the company behind ChatGPT and their family of AI models, including GPT-4, GPT-4.1 Mini, and GPT-3.5. The narration highlights that we'll be working with the Python OpenAI library, which acts as a bridge between our code and OpenAI's server. With that context set, we move into task 1. In this task, we're asked to open up a Python script and complete the missing imports. Specifically, we need to import the OpenAI library and the OS library. After completing these lines, we run the script to make sure that the libraries are properly installed and ready to use. If everything is correct, the program confirms that the import works. Here, we transition to authentication and client setup. Here, the lab explains the importance of an API client, an API key, and the base URL. The API key works like a password that identifies us and grants access, while the base URL defines the server location where requests are sent. This prepares us for task 2. In task 2, we open another Python script and are asked to initialize the client by plugging in the correct environment variables. This involves making sure we pass the OpenAI API key and OpenAI API base. Once those values are filled in, we run the script to verify the client has been properly initialized. If done correctly, the script confirms the connection to OpenAI's servers. Once the setup is complete, we move on to the heart of the lab, making an API call. Before jumping into it, we learn what chat completions are. This is OpenAI's conversational API, where we send messages and receive messages just like a chat. The lab explains the 3 roles in a conversation: system, user, and assistant, and how the request format looks like in Python. That takes us to task 3. Here, we open the script, uncomment the lines that define the model, role, and content, and then configure it so the AI introduces itself. Once we run the script, if all is correct, the AI should respond back with an introduction. This is the first live call to the model. Next, we're guided into understanding the structure of the response object. The lab breaks down the response path, showing how we drill down into the response choices message content to extract the actual text returned by the AI. Although the response object contains other fields like usage statistics and timestamps, most of the time, what we really need is the content field. That brings us to task 4, where we're asked to update the script to extract the AI's response using the exact path. Running the script here confirms that we can successfully capture and display the text that the AI returns. Once we've mastered making calls and extracting responses, the lab shifts gears to tokens and costs. We learned that tokens are the pieces of text used by the model that every request consumes tokens. Prompt tokens are what we send in, completion tokens are what the AI sends back, and total tokens are the sums of both. Importantly, output tokens are more expensive than input tokens, so being concise can save money. Finally, in task 5, we're asked to extract the token usage value, prompt completion, and total tokens from the response. The script is already set up to calculate costs, so once we complete the extraction and run it, we can see exactly how much the API call costs. The lab wraps up by congratulating us. At this point, we've verified our environment, connected to OpenAI, made real API calls, extracted responses, and calculated costs. The key takeaway is remembering how to navigate the response object with response.choices.message.content. Some of the finer points and details, like exploring usage fields or playing with different models, are left for you to explore yourself. But by now, you should have a solid foundation for working with AI APIs and be ready for what comes next in the upcoming labs. Alright, let's start with the lab. In this lab, we're going to explore LangChain and understand how it makes working with multiple AI providers simpler and faster. The key idea here is that instead of being locked into one provider's SDK and rewriting code whenever you switch, LangChain offers one interface that works everywhere. With it, you can move from OpenAI to Google's Gemini or xAI's Grok by changing just a single word. We begin the environment verification. In this step, we're asked to run a script that checks whether LangChain and its dependencies are installed. Valid SDK and rewriting code whenever you switch, LangChain offers one interface that works everywhere. With it, you can move from OpenAI to Google's Gemini or xAI's Grok by changing just a single word. We begin the environment verification. In this step, we're asked to run a script that checks whether LangChain and its dependencies are installed. By now, you should have a solid foundation for working with AI APIs and be ready for what comes next in the upcoming labs. Alright, let's start with the labs. In this lab, we're going to explore LangChain and understand how it makes working with multiple AI providers simpler and faster. The key idea here is that instead of being locked into one provider's SDK and rewriting code whenever you switch, LangChain offers one interface that works everywhere. With it, you can move from OpenAI to Google's Gemini or xAI's Grok by changing just a single word. We begin the environment verification. In this step, we're asked to run a script that checks whether LangChain and its dependencies are installed, validates our API keys and our base URL, and confirms that we have traditional OpenAI SDK approach with LangChain. We have to write 10 or more lines of boilerplate code just to make an API call. If we want to switch to another provider, we have to rewrite all of it. With LangChain, the same logic is cut down to just 3 lines. And switching providers is as simple as changing the model name. In this task, we're asked to complete both versions in a script and then run them side by side. This is where we really see the 70% reduction in code. The second task demonstrates multi-model support. Here, we're asked to configure 3 providers: OpenAI GPT-4, Google's Gemini, and XAS Grok, all with the same class and structure. Once configured, we can run the exact same prompt through all of them and compare their responses. This is especially powerful when you need to do A/B tests or balance costs, because you can evaluate multiple models instantly without changing your code structure. In the third task, we're introduced to prompt templates. Instead of writing separate hard-coded prompts for every variation, we create one reusable template with placeholders. Then we can fill in the variables dynamically, just like f-strings in Python. This eliminates the nightmare of maintaining hundreds of slightly different prompt files. After completing the template, we test it with multiple inputs to see how the same structure generates varied responses. The fourth task takes a step further by introducing output parsers. Often, AI responses are just free text, but what our code really needs are structured objects. Here, we're asked to add parsers that can transform responses into lists or JSON objects. In this way, instead of dealing with unstructured sentences, we can access clean Python lists or dictionaries that our application can use directly. Finally, we reach task 5, which is all about chain composition. LangChain allows us to connect components together with pipe operators, just like Unix pipes. Instead of writing multiple variables for each step, creating a prompt, sending it to the model, getting a response, and parsing the result, we simply chain everything together. With one line, we can link prompts, models, and parsers, and then invoke the chain to get the structure outputs. It's a much cleaner and more scalable way to build AI pipelines. By the end of this lab, we learned how LangChain reduces boilerplate, enables multi-model flexibility, creates reusable templates, parses structured outputs, and ties everything together with elegant chains. Some of the finer details, like experimenting with more complex parser setups or chaining additional steps, are left for you to explore on your own. Now we come to the technique. But it's not a technique in the sense of building LangChain application like we just did. No, we're talking about a technique that involves how you send your prompt to the agent that we just built. In other words, prompt engineering. When you send a prompt as an input to TechCorp's AI document assistant that we just built, the quality of your prompt directly impacts the quality of responses you receive. While AI agents can certainly handle a wide range of prompts, understanding prompt techniques help you communicate more effectively with TechCorp's system. For example, if you prompt the agent with this question, "What is the policy?" it can pull a lot of details that are irrelevant. Sending a more specific prompt like, "What's the company's remote work policy for international employees?" will lead to a more accurate result from the agent. And the same thing applies to role definition when you're describing the role of the agent. For example, you might descriptively write out a detailed prompt like, "You are a TechCorp customer support expert." When you're asked about the company's policy, you are to always respond with bullet points for easier readability. As you can see, being able to control the agent's behavior can directly benefit from a well-written prompt. This type of technique is referred to as prompt engineering. And there are different prompt techniques like zero-shot, one-shot, few-shot, and chain-of-thought prompting have its own use case for the task. For example, zero-shot prompting means that we are asking AI to perform a task without providing any examples. So if you send a prompt, "Write a data privacy policy for our European customers," you're essentially relying entirely on the AI's existing knowledge base to write the data policy document, since within the prompt, we're not giving any examples of what they are. One-shot and few-shot prompting is similar to zero-shot, but in this case, we're providing examples of how the agent should respond directly within the prompt. For example, you might say, "Here's how we format our policy documents. Now write a data privacy policy following the same structure." Because you've provided a template, the AI follows your specific formatting and style preferences more consistently. And conversely, few-shot learning is the act of learning from the LLM side, where even though the LLM might not have seen the exact training data for how to process your unique request, it's able to demonstrate the ability to fulfill your request from similar examples provided. For example, instead of prompting the AI agent with fix our data retention policy, you might instead use chain of thought prompting to say, here's how you fix data retention policy. Review current GDPR requirements for data retention periods, then analyze our existing policy for specific gaps, then research industry best practices for similar companies, and finally, draft specific recommendations within implementation steps. Now, fix our customer policy. As you can see, providing how LLMs should go through in breaking down the specific requests for how data retention policy should be fixed gives an exact blueprint for how the LLM should then go and fix the customer policy, which in this case, we're not explicitly telling the agent how to fix the policy for that, but it gives the reasoning steps for the model to fix it accordingly. So, in this lab, we're going to master prompt engineering using LangChain. The main problem being addressed here is that AI can sometimes give vague or inconsistent responses or not follow instructions properly. The solution is to use structured prompting techniques, zero shot, one shot, few shot, and chain of thought, each of which controls the AI's behavior in a different way. We begin by verifying the environment. The provided script checks that LangChain and its OpenAI integrations are installed, confirms that the API key and base URL are set, and ensures that prompt template utilities are available. Once this verification passes, we're ready to move into tasks. The first task introduces zero-shot prompting. In this exercise, we're asked to compare what happens when we provide a vague instruction versus when we write a very specific prompt. For example, simply asking the AI to write a policy results in a long generic essay. But when we specify write a 200-word GDPR compliant privacy policy for a European customer with 30-day retention period, the response is focused, useful, and aligned to the constraints. This demonstrates why being specific is crucial in zero-shot prompts. The second task moves on to one-shot prompting. Here, we provide one example for the AI to follow, almost like showing a single template. For example, if we give the AI one refund policy example with 5 structured sections, we can then ask it to produce a remote work policy and it will replicate the same style and structure. This shows how one example can set the tone and ensure consistency across many outputs. Next, in task 3, we expand on this with few-shot prompting. Instead of one example, we provide multiple examples so the AI can learn not only the format, but also the tone, pattern, and style. For example, giving 3 examples of emphatic support replies teaches the model how to handle customer support issues consistently. Once the examples are in place, the AI can generate new responses that follow the same tone and structure, making it especially powerful for use cases like customer service. In task 4, we're introduced to chain of thought prompting. This technique encourages the AI to show its reasoning step by step. Instead of vague one-line answer, the AI breaks a problem into steps and works through it systematically. This results in clear or more reliable and more accurate outputs, particularly for complex reasoning tasks. Finally, task 5 brings all of these techniques together in a head-to-head comparison. We run the same problem with zero-shot, one-shot, few-shot, and chain of thought prompts to see the difference. Each approach has its strength. Zero-shot is quick. One-shot ensures formatting. Few-shot enforces tone and consistency. And chain of thought excels at detailed reasoning. The outcome shows that choosing the right technique can dramatically improve results depending on the task. We not only learned what each prompt method is, but we've also seen them in action. The key takeaway is that the right technique can make your prompts 10 times more effective. Some of these exercises are left for you to explore and refine. But now you have the foundation to decide whether you need speed, structure, style, or reasoning in your AI responses. That wraps up this narration. And with it, we're now ready to move on to the next lab onto vector databases and semantic search. Let's do a quick recap of what we just built. We learned about what LLM is and how LLMs use what's inside the context window. After learning about LLMs, we wanted to solve TechCorp's business requirements of searching for 500 gigabytes worth of data. In order to do that, we determined that embedding is a good way to search a massive set of documents. After that, we went over LangChain and what functions they serve, which is that they allow us to easily build agentic applications like TechCorp's chatbot. So now that we have the LangChain application, we need to be able to search through these large sets of documents. Let's say inside the 500 gigabytes of documents, your company has a document called Employee Handbook that covers policies like time off, dress code, and equipment use. It Building a database around this requirement can be tricky. In a conventional approach, where data is stored in a structured database like SQL, you typically need to do some amount of similarity search, like select all from documents, content like vacation or vacation policy with a wildcard before and after to look for details about questions on holiday. To expand your result set, you might increase the scope by adding VZ or VAC space POL. However, the drawback to this approach is that it puts the onus on the person searching for the data to get the search term formatted correctly. But what if there was a different way to store the data? What if instead of storing them by the value, we store the meaning of those words? This way, when you search the database by sending the question itself of, can I request time off on a holiday, based on the meaning of those words contained in the question, the database returns only relevant data back. This is the spirit of what vector databases tries to address, storing data by the embedding. So essentially, instead of searching by value, we can now search by meaning. Popular implementations of vector databases include Pinecone and ChromaDB. These platforms are designed to handle embeddings at scale and provide efficient retrieval based on semantic similarity. And these are also great use cases for prototyping something quick. While conceptually this seems straightforward, there's a bit of an overhead in setting this up. And you might be asking, well, can we just throw the employee handbook into the database like we just did for SQL database? Not quite, and here's why. With SQL database, the burden is put on the user searching to structure the database. But with vector databases, the burden is put on you who's setting up the database, since you are trying to make it easier for someone searching for the data. And you can imagine why a method like this is becoming extremely popular when paired with large language models and AI, since you don't have to train separately on how LLM should search your database. Instead, the LLM can freely search based on meaning and have the confidence that your database will return relevant data it needs. So let's explore some of the key concepts behind what goes into setting up a basic vector database. Let's start with embedding. Embedding is really the key concept that makes the medium go from value to meaning. In SQL, we store the values contained in the employee handbook as a straight up value, but in a vector database, you need to do some extra work up front to convert the value into semantic meanings, and these meanings are stored in what's called embeddings. For example, the words holiday and vacation should semantically share a similar space, since the meaning of those words are close to each other. So before the sentence, employees shall not request time off on holidays, in the document is added to the database, the system runs through an embedding model. And the embedding model converts that sentence into a long vector of numbers. And when you search the database, you are actually comparing this exact vector. That way, when someone later asks, can I take vacation during a holiday, even though the phrasing is a little bit different, the database can still service the request. And this is the fundamental shift. Instead of searching by exact wording, we're now searching by meaning. Another important concept is dimensionality. And you might be asking, why do I have to worry about dimensionality? Can't I just throw the words into embedding and store it into the database? There's one more aspect in embedding that you need to think about, and that's dimensionality. Typically, a word doesn't just